All right, guys, we're gonna see if we can make this video lesson work for today. Take my mask off. Considering I'm absent, I'm gonna record myself so you guys have access to the instruction for scientific notation, which is our next topic. Objectives for today, we wanna be able to understand what makes a problem written in scientific notation simplified, or I should say kind of define what scientific notation is. Work on writing numbers in scientific and then converting them back to standard notation, which if you're wondering what standard notation is, basically any number that you're used to seeing is called standard, and any number that you are maybe not as used to seeing is called scientific, or we'll call that scientific notation for today. So that's our topic, all right? This is something you may have seen before. We're going to kind of take a spin to it based on what we've been talking about recently that might make it just a little bit different, all right? But scientific notation by nature is just a different way of writing numbers. So it's a way of typically expressing very, very big or very, very small numbers. Okay, very big or very small. Okay. Normally, what we see is we see a base letter or base number A, and we multiply it by some factor of 10 raised to the n power. This is kind of your standard scientific notation number. This value of A, however, must be between 1 and 10. Okay, that's kind of one of the bits of criteria for scientific notation is your base has to be between 1 and 10. The only other criteria is that n has to be an integer. Which, if you remember, is just like your counting numbers plus their opposites. Okay, so if we continue these on in both directions, those are what integers are. Some examples of numbers in scientific notation, 3 times 10 to the 7th power, okay? 4.1 times 10 to the negative 3rd power. These are both scientific notation numbers. And since I did say we use them to represent really big numbers and really small numbers, generally, if the exponent is positive of the factor of 10, that's representing a very big number. Okay? If the exponent is negative, this is representing a very small number. Because as we've learned in this unit, negative exponents don't necessarily represent negative numbers, they just represent reciprocals of other numbers. So that 4.1 times 10 to the negative 3rd power is literally 4.1 times 1/1000th, okay, which is making that number pretty small. 3 times 10 to the 7th power, however, is 3 times 1 with 7 zeros after it, which is, I think, like 1 million. Okay, so that's a really big number. Typically, scientists will use this type of notation for, let's just say, distance from Earth to Jupiter, or another scientist might use it to measure the width of a cell, right, which would be a super small value, but we still have to be able to represent it, okay? So just recognizing scientific notation, we look at this number, 53 times 10 to the 4th power. This is not written properly, okay? And the reason why this is not scientific notation is that the value of 53 is not between 1 and 10. Okay, we could convert it if we wanted to, but as of right now, all we're trying to do is recognize scientific notation when it presents itself. Okay, let's look at some others. 3.42, we look at the base number. This is between 1 and 10, and negative 7 is an integer. So yes, this is scientific notation. All right, some other examples, 0.035 times 100. Okay, again, not in scientific because this number is not between 1 and 10, okay, and 100 is definitely not a factor of 10. Or at least it's not written as a factor of 10 or a power of 10. You could convert 100 to 10 to the 2nd power and then do some work with this, but as of right now, it's not properly written in scientific. Okay? So you might ask, how do we do it? All right, how do we make a big number like this, right? This is 1,430,000,000 and convert the thing into scientific notation. And it's actually pretty easy. First thing we do is identify our base number, all right? we identify A. And A, as I said, is a number that's between 1 and 10 that you kind of see within the number. So when I look at this, I start moving my decimal point and moving it, and I see that if I place my decimal right here in that spot, my base number could be 1.43. It's a number between 1 and 10. And after I've placed my decimal, to write this in scientific notation, I just need to count place value spots past the decimal. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 place value spots past the decimal. So we would write this as 1.43 times 10 raised to the 9th power. Okay? That's 1.43 billion. All right? So it's pretty easy. Here we got a really, really small number, and that base number that we see here is going to be right here. That's the number 1. Okay? And all we need to do from there is just count decimal spots. If we place it here, we need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 spots back. Actually, we'll just call this 10 spots back. Let me just make sure on this one. Sometimes I confuse myself. Sometimes I do the swoops too. The swoops can help. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This would be to the 10th power. And since it's a really, really, really small number, I'm going to use a negative 10th power. Okay, this is 1 times 10 to the negative 10th. Generally speaking, if the number is going to be bigger than 1, you'll use a positive exponent. If it's going to be less than 1 and greater than 0, so a really, really minute number, you're going to use negative exponents to represent them. Okay? 678,000, again, identify your base number. I place it right here, and then make your swoops. So we go 1, 2, 3, 4, and 5 spots. So this would be 6.78 times 10 raised to the 5th power. 10 to the 5th power is 100,000. Okay? So this is like 6.78 times 100,000, or 678,000. So we can easily write numbers that exist, whether they be really big or really small, in scientific notation, just by kind of understanding that tens place and understanding what direction we're moving. Okay, the last example, 0.000032, small number, my base number would be 3.2, and then I would just move my swoops, move my decimal point, 1, 2, 3, 4, and 5 spots. So this is 3.2 times 10, and notice we got a really small number to the negative 5th power. All right, so just a little recap. You guys may have seen this type of notation before, maybe you haven't, but it's super helpful when dealing with computations with really big and small numbers. Okay, let's take it the opposite direction. We give you a number in scientific and ask to write it in standard. So the way that I like to do it is I like to write out my base. So this is 5.5, and then I imagine that if I'm multiplying this by 10 to the 6th power, that I move 6 places to the right. So I'm going to move my decimal from here, and I go 1, 2, 3, 4, 5, and 6, and then I just add zeros in my swoop. So I got a 0 here, a 0 here, a 0 here, a 0 here, and a 0 here. And then, add our commas. So we've got a comma in this spot. This is 5,500,000, okay, or 5.5 million. So it's all about place value points. Notice how I did not just add 6 zeros at the end of 5 and 5. I moved the decimal 6 spots. It takes me 1 spot to get to kind of the quote-unquote end of the number, and then I add 1, 2, 3, 4, 5 zeros. Okay. Here's a really small number. Again, start with your base. We've got 3 and 1, and since this is represented with a negative exponent, we're just going to move the decimal the opposite way. So I'm going 1 spot to get here, and then just adding some zeros. There's 2, there's 3. Put my decimal point in, and I've got my answer, 0.0031. Like I said, a really, really small number. Okay, you guys can pause this and try it on your own if you'd like to. Grab my 4 and my 6. I've got negative fifth power, which means I'm just moving it this way. I'm moving it to the left. I move left 1 to get to negative, to move 1 spot, and then I need to go 1, 2, 3, 4 more. Okay. Final answer here is 0.000046. Super small number. Last example, 3.8 times 10 to the 12th power. You can kind of just imagine how many zeros you need to add at this. This is an extremely large number. So we're going to move the decimal 1 this way. So we got 3, we got 8, and then I need to add 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then your commas. Don't know if in Schoology you guys need to add the commas or not. It does help you to conceptualize the number. That's 3,800,000,000,000. If I'm counting my zeros right. Super big number. All right. How can we compare these numbers? So we've got a mixture of numbers that are raised to the 7th and then raised to the 8th power. What we're going to try and do is order these from the least number to the greatest number. Now, if everything's properly written, it's pretty easy. 10 to the 7th power is a smaller number than 10 to the 8th power. So I know that my 10 to the 7ths have to be in my least category, and then I can just look at the bases. Okay, we've got 1.41 versus 7.49. 1.41 is a smaller number. So we got 1.41 times 10 raised to the 7th as my smallest number of this set, followed by 7.49 times 10 to the 7th power, and then I move on to my 10 to the 8th powers, and I just need to look and say which of these two values, 1.06 or 1.8, is a larger value, which would obviously be 1.8. So my next number in the set would be 1.06 times 10 to the 8th power. The last number in the set would be 1.8 times 10 to the 8th. All right, so you can really quickly order numbers that are written in scientific just by looking at the exponents first and then your base number second. All right, here are a bunch of negative exponents. So again, if we're trying to go from least to greatest, all right, if we're trying to go from least to greatest, now here we're looking for the smallest exponent, which is actually negative 28, right? This is a smaller exponent, negative 28 than negative 24. So we're going to start there. 9.109 times 10 raised to the negative 28th power is the smallest number of this set. The next smallest number of this set would be anything with a 10 to the negative 24th power. Okay. So of those two numbers, I know that 1.673 is smaller than 1.675, so that's my next number in the set. 673 times 10 to the negative 24th. And the largest number of this set, even though they're all very, very small, minute numbers, is my 1.65, 675. 10 to the negative 24th. Okay. We can also perform some different operations, okay, with numbers in scientific, and this actually plays into what we've been talking about in math pretty clearly, right, or pretty directly. If you guys remember, we talked about multiplying powers with the same base in lesson 2. Well, here we've got two powers that have the same base, and notice how we also have a whole bunch of multiplication happening here. So basically, when we're multiplying numbers, we can group the base numbers together and do those first. We got 3 times 5, and we'll group those together. We then have our 10s raised to the 5th power and 10 raised to the negative 12th power. So it helps us to multiply these numbers in this manner because 3 times 5 is easy enough. That's 15. 10 to the 5 plus negative 12 power is going to be 10 to the what? Negative 7th power. Now, you guys might be thinking to yourself, Neubauer, 15's too big. all right, which is 100% true. 15 is too large of a base because it is not between 1 and 10, so this is how you handle that. 15 itself can be written in scientific. That would be 1.5 times 10. It's another way of writing the number 15. Well, if you take 10 to the first power and times it by 10 to the negative 7th power, we add these exponents together to get 10 to the negative 6th. So we got 1.5 times 10 raised to the negative 6th power, all right? Generally speaking, this is a good way to think of it, is if your base number is too big, bump it up. Bump the exponent up 1. Notice how negative 6 is 1 greater than negative 7. If the exponent is too small, if the base number is too small, bump that exponent down, okay? We are kind of giving a factor of 10 to our 10 to the negative 7th from the 15, okay? If you want to think of it that way, that can be helpful. All right? This problem here, we got two really large numbers. 7 times 10 to the 8th is an enormous number, times another relatively big number. We just group the base numbers together. 7 multiplied by 4 is going to group together. And we group our 10s together. 10 to the 8th and 10 to the 5th power. We do the math here. 7 times 4 is 28. Times 10 to the 8th plus 5 power, that's 13th. Okay, again, we've got the base number being too big. Okay, 28 is far too big, so we change that to 2.8. And since we only had to move the decimal once to get to 2.8, we're going to bump the exponent up by 1. 10 to the 14th power. Okay, again, it has a factor to give. It can give a 10 away. It doesn't need to take a 10. All right, so you can perform a lot of different operations with numbers in scientific, just using some of the rules we've been practicing with. All right, I want you guys try this one out completely on your own. Okay, pause it if you need to. And then I'll work it out shortly after. So first thing we would need to do is multiply the bases together. So I'm just going to do that over here, kind of the old traditional way. 5 times 3 is 15. 3 times 1 is 3. With a 1, that's 4. 2 times 5 is 0 with another 1 on top there. 2 times 1 is 2, plus 1 is 3. Add them all up. All right. And we've got, let's see, 1, 2, 3 spots. We got to move this over 3 spots. 1, 2, and 3 spots. Ooh, 0.345. So 0.345 multiplied by 10 to the 5 plus 3 power. Now, this is a situation that's a little bit different. Now, our base number is too small. So what we're going to do is we're going to send a factor of 10 from our tens place, okay? And we only need 1, and what that's going to do is bump this exponent, or this decimal point over 1. We would have 3.45, and since we sent one factor of 10, we now have 10 to the 7th power as our final answer. Okay, now our base is between 1 and 10, and our 10's raised to the integer exponent. We're good. All right. So a lot you can do with this. I won't rep through all of these. You can raise them to a power. If you guys remember this rule, powers of powers, or powers, I guess, technically of products. Here's our A and here is our B. So if you guys remember the rule, A times B to the X power, we did what was similar to the distributive property where the X exponent needs to apply here and here. We got A to the X times B to the X power. Okay, so that's kind of what we did with that. Well, we're going to do the same thing here. This is a really big number times itself, by the way, so our result is going to be really big. We got to apply the 2 to the 8, and then we also have to apply the 2 to the 5. So that's 8 squared times 10 to the 5 times 2 power, or 10 to the 10th. And then we just simplify. 8 squared is 64. 10 to the 10th power. 64 is just one factor of 10 too big. It's got an extra factor to give, so we're going to pass this one over. Our final answer, 6.4 times 10 now to the 11th. Again, that base was too big. We bumped it up. All right. So regardless of what operations you're doing with scientific notation, you got a lot of similar properties to what we've been learning about. All right. Here we're going to apply this fifth exponent to everything. Okay, apply it here and here. This is 2 raised to the fifth times 10 raised to the negative 8 times 5. That's negative 40th power. Big number. I should say really small number. Very small exponent. 2 to the fifth power, that's 2 times 2 is 4, times 2 again is 8, times 2 again is 16, times 2 again, I think this is 32, times 10 to the negative 40th. And remember, if that base is too big, give a factor, okay? You can give a factor of 10, and now we would bump that to 3.2 times 10 to the 1 greater than negative 40th power. Which, just watch your math here, 1 greater than negative 40 is negative 39. All right, put a bow around it, and we're good. All right, good to go. I mean, we can do these all day. Dividing is actually also very possible with numbers in scientific notation. All right, let's take a look at 1 or 2 like this. Now, if you guys remember, from the last lesson that we had, dividing powers, we can split up our division. We can do our division in 2 parts. So we're going to do the same thing here. We're going to divide 2.5 by 5.0. All right, and then take a look at our tens. This is going to be multiplied by 10 to the negative 3 minus negative 8 power. Well, 2.5 divided by 5.0 is a fraction. That's the same as 25 fiftieths, or 0.5. All right, now we need to do the math with that negative. Negative 3 minus negative 8 is the same as negative 3 plus positive 8. So that would be 10 to the 5th power. Now, when you're finishing up with these, you always have to ask yourself, is the base between 1 and 10? And if it's not, you need to make that adjustment. All right, 0.5 is less than 1. So that means we got to send a factor from the tens. Okay, we only need to send 1, but that would move this decimal over, and we would write this as 5 times 10 to the 1 less than 5th power, 10 to the 4th power. Which, by the way, is like 50,000. All right. So I know this is kind of a heavy content day. We did a lot with scientific notation, introduced the concept, which I'm guessing you guys have at least seen numbers in scientific before, maybe not necessarily known what they are. But just know we can do all sorts of operations with really big and really small numbers quickly understanding this skill. 3.6 divided by 9. Multiplied by 10 to the negative 3 minus 4 power. By the way, just a quick way to do 3.6 divided by 9, move the decimal over in both of these and simplify the fraction 36 90ths. I think 9 goes into both of those, and you'll get 0.4. All right, I'm just going to give you that one. This is 0.4. Multiplied by 10 to the negative 3 minus 4 power. That's negative 7th power. So again, we're in a situation where our base is too small. All right, so we have to take a factor. Okay, that will make this 4 multiplied by 10 to the 1 less than negative 7th power. Think in your head now, what's 1 less than negative 7? And that would be negative 8th power. Right. So I know this was kind of a quicker lesson today about scientific notation in terms of how to use it. hopefully it was helpful. Today you guys have similar things. You got a puzzle piece assignment and a formative. Let's get to work.